Good morning, all of you. The last lecture for power diodes, we have seen the VI characteristics. Now, the power diodes have another type of characteristics which are called as reverse recovery characteristics. Now, these characteristics are associated with the charge, current, and time. These three parameters are important. That is charge, then current, and time. Now we know that these three parameters are associated with each other. We denote charge to be Q, we denote current to be I, and then time to be small g. We know the relation between charge, current, and time. That is, we define current to be rate of flow of charge. Correct? Or charge is the product of current and time. And the characteristics today which we are going to discuss, the reverse recovery characteristic, are associated with these three parameters of power diode. Now, suppose a diode is in normal operation. When we say power diode is in normal operation, it carries current. It carries current from anode to cathode when the power diode is in normal operation. So we call that current to be forward current, IF. And then if we allow that current to decay, that is to decrease. Now initially when I said the power diode is conducting normally, we'll get some constant current. If the losses are supposed to be negligible for forward current conduction, then we say we get almost a straight line with respect to time of forward current. Now you can observe this part of the characteristics which I have drawn on the board. So in this part, for this duration, the current is constant. Means we are getting normal current, normal forward current from anode to cathode. And after that particular instant, by somehow, if we allow that current to decay, now when we say decay, we will just remove the biasing from the power diode. Okay? Or we just start removing the biasing across the power diode. So what will happen to the current which is normally flowing from anode to cathode? It will start to decay. Now how it will decay? It will decrease like linearly with respect to time, and at some particular instant it will become zero. Now real story starts after the instant when the forward current decays to zero, and it continues to flow even if it becomes zero. And that's the story of reverse recovery characteristic of power diode. Now what is expected normally or ideally when the forward current is unbiased and the current allows to decay up to zero, the moment at which the forward current becomes zero, it should stop. That is an ideal condition. But since the power diodes, they have the semiconducting material in them, during conduction what happens? The charge is stored in the vicinity of semiconductor devices. And because of that charge, what happens? The current doesn't stop even if it crosses the zero, it continues to flow in the reverse direction. So, so what happens with that? It will ideally not be zero. It will go like negative for some instant. And after that, at a particular instant, it will become maximum in the reverse direction, and from that value again it will start to decrease. But this process goes continuously for a particular time, to which that time is called as reverse recovery time, which is denoted by, let us say, TRR, reverse recovery time. Reverse recovery time is the duration when the current crosses zero, when the diode current allows to decay and it crosses to zero, and it continues to flow even after it crosses to zero, and then it becomes zero or normal. That duration for which these events happens is called as reverse recovery time. And as I told you, the reason behind this is the charge stored in the vicinity of semiconductor devices. Now, this reverse recovery time recovers the charge which is stored, or during this reverse recovery time, the charge is recovered which is stored in the semiconductor device when it was in the normal operation. That charge is called as reverse recovery charge, which is denoted by QRR. So, as I told you, the phenomenon of reverse recovery characteristic depends on the three parameter: time, charge, and since these two things are associated with the current, which is normally called reverse recovery current, IRR. So, the reverse recovery characteristics are associated with the charge, current, and time. More specifically, the reverse recovery characteristics are associated with three parameters called reverse recovery time, reverse recovery charge, and reverse recovery current. So these three parameters are very, very important for reverse recovery characteristics of power diode. Now, the another characteristics which we already have studied, VI characteristic. Now, VI characteristic stands for the forward voltage across the diode and the current through the diode. Now, we must know with which two parameters, or with which parameters actually the characteristics are dependent. Reverse recovery characteristics are dependent on, more likely, reverse recovery time, reverse recovery charge, and reverse recovery time. So we have to get introduced with these three concepts. What do we mean by TRR? What do we mean by QRR? And what is actually IR? Okay. So TRR is the duration when the current decays to zero and it becomes normally zero. So during this reverse recovery time, the charge stored in the vicinity of semiconductor device, it is recovered. Okay. So that charge is called as reverse recovery charge, and the current conduction during this time interval is called as reverse recovery current, IR. Okay. Now, going into the details of reverse recovery time, it can be split in two components. It can be split in two components. Here you may observe that TRR is the total time of reverse recovery. We call it as a reverse recovery time. Now it has two parts. In one part, which I have shown with the straight line, that is the shaded part. Okay, and the another part which I have shown with the dotted part or dotted region. So in this particular region, what happens? There are two things happening during this interval. during this interval. Couple of things are happening. The first thing is the charge is to be recovered is the main concept. Charge is to be recovered during total time TR. Now, how that charge is recovered? That charge is recovered in two steps. In the first step, the charge stored in depletion layer is recovered, because we know that the power semiconductor device has the depletion layer. I will show here with this shaded part. This is depletion layer and this is P and N. Normally this is normal diode, but for your understanding purpose I am just drawing this because the structure of power semiconductor device is something different. But only thing is that you need to understand the concept. That's why I'm drawing this the normal diode structure. Okay, so in this part we have charge. So that charge is recovered in the first step. So this part indicates the charge recovered by recombination of the opposite charges. Now, how charge is recovered actually? What is the physics behind recovering of the charge? Because we know that in semiconducting material there are p-type holes. In p-type there are holes, in n-type there are electrons, and naturally or spontaneously they should get combined with each other. Okay, that is the process. So when they get combined each other, what happens? The charge is recovered. That is the concept. So that natural behavior of recombining with each other and recovering the charge, that process is happening actually in this part during TRR, to which we called as a to which we are calling as a reverse recovery time. Okay, in which the charge is recovered. In the first step, how the charge is recovered, or from where the charge is recovered? Charge is recovered from depletion. Okay, so this process of recovering the charge from depletion layer requires the time component called TA. Okay, now since it has the second step, in the second step of charge recovery, of reverse recovery charge, is charge stored in the vicinity of semiconductor devices. Vicinity of semiconductor device or power diode. Vicinity of power diode. Because the main body of the power diode is p-type material and n-type material. Now, in the second step, what happens? The charge is recovered in these two parts or from these two parts. Okay, and for which it will require some time. We will say TB. So TA is the time associated with depletion layer, during which the charge stored in the depletion layer is recovered. Okay, and TB is the time associated with the vicinity of power diode, during which the charge stored in the vicinity of power diode is recovered. So in both the processes, what is happening? The charge is getting recovered. Okay, so I'll say QR1 is the charge recovered during time interval TA, and QR2 is the charge recovered during time interval TB. So what is the total charge recovered? QRR is equals to QR1 plus QR2. Okay, and for which it requires the total time period TRR. TRR is equals to TA plus TB. Okay, so you can say QA is the charge recovered from time interval Ta, and Qb is the charge recovered from Tb or during time interval Tb. So QRR is equals to Qa plus Qb, and TRR is equals to Ta plus Tb. That is, I must write here Qa, and this is Qb. Okay. So what is the total charge recovered? Qa plus Qb, small. Okay. So QRR is the charge recovered. TRR is the time required to recover that total charge in two steps. In the first step, the charge is recovered from depletion layer. In the second step, the charge is recovered from the vicinity of semiconductor device. Okay. So now we get this characteristic because of recovering of the charge during the conduction of diode, where diode current allows to decay. So it will decay. Decay means to decrease. It will decrease to zero. But normally or ideally it should be zero because we want to make it zero. But since there is a physics behind semiconducting material or semiconductor devices, that physics won't allow that current to be there zero. Then it will take some time to make it zero. So it will make that diode current to flow even if it becomes zero in the reverse direction. And in that, what happens actually? The charge is recovered. Charge is recovered from depletion layer. Charge is recovered from the vicinity of power semiconductor device or diode. Okay. So as a result of this operation, we gain these characteristics. Okay. But analysis of this reverse recovery characteristics are something different. It doesn't go so ideally because we say the total reverse recovery time is the time interval at which the current decays to zero and continues to flow, and again it becomes zero. But the actual definition or the analysis of reverse recovery time is that the time interval when the forward current crosses to zero to the time interval when the reverse current IRN becomes its 25% of its maximum value, or the reverse current IRR becomes 25% of its maximum value, is 0.25 into IRN. Okay, IRN is the peak value of the reverse current, and here we get the 25% of the maximum value. Okay, so reverse recovery current should exist. Then and then only we can call. So in that duration, we can define the reverse recovery time. Okay, so it doesn't mean that the standard value of reverse current should become zero. No, the reverse current will become like 25% of its maximum value. So the time interval at which the forward current decays to zero and the time interval at which the reverse recovery current will become 25% of its maximum value. This time interval is called as reverse recovery time, and the charge recovered in that duration is called as reverse recovery current, and the current during this interval is called as reverse recovery current. Okay, now we will just find out these parameters, because as I said, we are associated with QRR, we are associated with TRR and IRR. So we need to estimate the values of these parameters. What exactly, how we can calculate, like that. That type of analysis we are supposed to do here. Okay, so with the help of these characteristics only. Okay, we will take the help of this characteristic and we will find out what is QRR, what is TRR. At least these two parameters are important. And as I told you, these two parameters are associated with IR. Okay, so मी सुरुवात कुठून केली होती की रिव्हर्स रिकव्हरी कॅरेक्टरिस्टिक ह्या तीन पॅरामीटरवरती अवलंबून आहे. डायोडच्या. एक म्हणजे चार्ज की ज्याला मोर स्पेसिफिकली रिव्हर्स रिकव्हरी चार्ज आहे, त्यामुळे आपण काय म्हणतोय QRR. दुसरा पॅरामीटर म्हणजे TRR, किती वेळेत तो चार्ज रिकव्हर केला जातोय, TRR. आणि त्या वेळेत किती चार्ज रिकव्हर केला जातो, RR, QRR. ओके. अँड या दोन पॅरामीटरमुळे डायोडच्या करंटवरती काय परिणाम होतोय, आणि तो करंट हा आपण कशाने दाखवतोय, IRR ने दाखवतो. म्हणजे तीन पॅरामीटर्स महत्वाचे आहेत. रिव्हर्स रिकव्हरी चार्ज QRR, reverse recovery time TRR, and reverse recovery current IRR. Okay, so I'm saying RR is nothing but reverse recovery. Okay, that's why specifically we are mentioning QRR, TRR, and IRR. Okay, so we'll find out these parameters, for which probably we will need to have some mathematics in place for analysis, for which you need to know the equation for straight line passing through origin, or area of triangle, because if you observe the characteristic below x-axis here, that is below time axis, this is time and this is current. Okay, so this part is important, this part during which the charge is recovered, this part which is associated with reverse recovery time, and this part is associated with reverse recovery curve. So we need to find out these three parameters based on these characteristics which we are observing here, and for which we need to apply some mathematics. Okay, now by observation, if I say this is the straight line, and if I assume this is to be shifted y-axis and this is x-axis, you know, this straight line passing through origin, we indicate this by the equation. Suppose this is y-axis, this is x-axis. So we write equation y is equals to m into x, where m is the slope, or y is equals to dy by dx into dy by dx. Okay, this is how we write the slope of this line. Okay, so or the equation of this line, mx plus c actually, but since this is assumed to be passing through origin, we will write y is equals to mx. So what is y here? Here y is current, because this is current. And what is x here? X is the time. So can I write this equation like the current, this is the straight line which indicates the current. So IRR is equals to di by dt. Now here the time taken to decrease is to IRM is TA or TRR. So this is the reverse recovery time, okay, which is on x-axis. So I must write here TRR into di by dt. Okay, now this time, let it be TRR or let it be TA and TB. We said TRR is equals to TA plus TB, but these two times are very small, and that's why we assume TRR to be here I should write TA into di by dt. So TRR is equivalent to TA. Okay, and that's why what I'm writing here, IRR is equals to TRR into di by dt. This is equation number 1. Di by dt is the rate of change of current with respect to time. So since we are dealing with the current with respect to time, so di by dt, TRR is the time. Okay, now you may call this as equation number 1. Now from this part of the characteristic, you may assume this is to be triangle, and the area of triangle is nothing but the charge recovered. Okay, how will you how will you estimate the charge recovered? Charge is nothing but the area under this curve. So you can write QRR to be area of this triangle. So how will you calculate this area of this triangle? This is approximately TRR, and this is what is the height of the triangle. So we normally calculate the area of triangle like 1 by 2 into base into height. Okay. From that you can write 1 by 2 base is TRR. Okay, just this is inverted triangle, so base is TRR and height it is IRM, or you can write IRR. Okay, reverse recovery curve. From this, TRR is equals to 2QRR divided by 2QRR divided by IR. Okay. Now here from equation number 1 we get TRR small r. Okay, TRR is equals to IRR divided by DI by GT. Okay, so equating these two equations, TRR and TRR, what we will get? We'll get like 2QRR divided by IRR is equals to IRR divided by DI by dt. Okay, so here QRR is equals to QRR is equals to QRR is equals to IRR square divided by 2 into DI by dt. Okay, IRR square. So from this equation, you will not be able to see here. You will write QRR is equals to I 1 by 2 IRR square into DI by dt. Okay, from that equation only you can convert like IRR is equals to, or I square R is equals to, IRR square is equals to 2 into QRR into DI by dt. So what will be IRR? IRR is equals to, we will find out the square root of this. So it is 2 QRR into di by dt 12. Okay, so this is the value of reverse recovery current. Okay, it is just mathematics for which we are using the equation of straight line here. Okay, now we are we are assuming that these two time intervals are very small, or the time interval required is very small, so you can assume Ta corresponds to TRR here. So you can replace Ta from that equation. So IRR is equals to TRR into di by dt. Okay. So this is what is the relation between here the reverse recovery charge, the rate of change of current, and reverse recovery current. Okay. So this is the analysis of reverse recovery characteristic. Obviously, I have presentation wherein you will see in a sequence these equations, so you may not get the correct uh, steps here, but you can just see which are the expressions we are getting. Okay, this expression is important. IRR is equals to square root of 2QRR
Sir,
and its square.
अ,
2 into
सर
QRR.
राईट साईडचं दिसत नाहीये.
Yes,
राईट साईडचं दिसत नाहीये बोर्डच्या.
great.
हा.
दिसत नाही. मला तर स्क्रीन मध्ये पूर्णपणे दिसतंय हे. रिफ्लेक्शन वगैरे येते का लाईटचं?
नाही अर्धच दिसतंय.
हो का? Is it fine? बरोबर आहे. Okay, you may write that expression. Even this is not written properly. Some steps are here and there, so you can write the expression or the analysis part through the presentation which I have. Okay, so I will share that presentation on the screen. So here you need to understand whether you have got the concept of reverse recovery characteristic. Okay, as I told you, these characteristics are associated with three parameters, and we need to find out how these parameters are to be calculated. Okay. So this concept depends on the physics of the semiconductor device, because we know that the power diode is combination of p type and n type of material of semiconductor, and naturally the current will not become zero even if we try to make it zero. Naturally there will be some things those they are happening in the device to recover the charge stored during the conduction of power. What is happening when we are getting that normal current to the power diode? So there is a storage of the charge. Charge is stored. Okay, charge is stored in the normal operation or during normal operation. And when we remove biasing from the power diode and when we allow the current to become zero or to decay zero, what happens due to this stored charge is the reverse recovery characteristic. That is, the stored charge will recombine with the opposite charges. Okay, so we could recover the charge, or the device itself will recover the charge itself, because this is a natural process. So it will recover the charge. So when diode is in the normal operation, charge is stored. When we allow diode to stop conducting, the charge is recovered. But charge recovered has two parts. One, the charge is recovered from junction or layer, depletion layer. and the another is the charge is recovered from vicinity. That is the main body of the power semiconductor device or power diode. So in these two parts, the charge is recovered, for which it will take time. So that time we calculate as a TR. Total charge recovered during that time we calculate it as a QR. And the current conduction because of this process, we call it as a IR, reverse recovery. So I conclude the explanation with we could get the understanding of what is reverse recovery time, what is reverse recovery charge, and what is reverse recovery current, and why this is happening. This is happening because of the physics of the semiconductor device. Physics behind semiconductor device. What is that physics? During conduction, charge is stored, and during the when the diode is removed from the bias, okay, or bias is removed, then diode stops conducting, but it doesn't stop conducting ideally. It will take some time to recombine the opposite charges, through which the charge is recovered, for which it will require time. The charge is recovered and we get some current even if the bias is removed. So this concept are specified, or this concept is specified by the reverse recovery characteristic, which we call as a power diode. Okay, most of the time they ask this question in theory as well as in practical, and for understanding what exactly happening with the power diode during reverse recovery process. So you can look into these concepts which are very important for power diode. And this is basic behind every semiconductor device, because the semiconductor devices we are using as a switch. When we are saying that the devices are used as a switch or switches, then there will be switching operation. Okay. Now, what do you mean by switching on and off? So in this part, the diode is conducting normally means diode is on, and in this part, diode is made off. So this is switching operation. But these characteristics are showing reverse recovery characteristic. That is another thing. But almost all the devices they work as a switch, and for which we need to plot the switching characteristics. Okay. Now for that, those switching characteristics are the resultant of this process. By somehow, this concept is associated with each and every semiconductor device. Okay. So let me start the presentation from which you will get these concepts more clear. So we have two types of characteristics in power diode. One is their characteristic and another is reverse recovery characteristic. So today we will be concentrating on reverse recovery characteristic. Power diode have the charge stored. Okay, where the charge is stored during the normal operation of power diode in the depletion layer and in the vicinity of semiconducting material. Okay, or device. The charge stored always experiences pressure to recombine with the opposite charges and get it neutralized. That is the natural behavior of the charge. So it will always try to get It's opposite charge for recombination. Okay. The process actually takes place after the diode current decays to zero, and it continues to conduct in the reverse direction. Okay. So this process will be there continuously even after the diode current decays to zero. Since the charge is recovered during the process, it is called as reverse recovery charge. Recover. So the process of recovering the charge is happening in this. So it is termed as a reverse recovery charge. ओके याला रिव्हर्स रिकव्हरी का म्हणायचं चार्ज रिकव्हर केला जातो म्हणून याला रिव्हर्स रिकव्हरी असं म्हणायचं सो इट टेक्स सर्टन टाइम कॉल्ड रिव्हर्स रिकव्हरी टाइम या प्रोसेसला काहीतरी वेळ लागतो तो वेळ म्हणजे रिव्हर्स रिकव्हरी टाइम या टाइम मध्ये काय केलं जातं चार्जला रिकव्हर केलं जातं ओके सो दीज आर द कॅरेक्टरिस्टिक द पार्ट ऑफ कॅरेक्टरिस्टिक ए इन दिस I have explained. B and C, these two characteristics are associated with voltage and current. Okay, so the first characteristic belongs to current versus time or represents current versus time, where the B part is the voltage with respect to time. We know if the current is present in the diode or the device, the voltage is almost zero naturally. Okay, if we neglect the voltage drop, but if there is a voltage drop, you may see some voltage is present, but ideally it should be zero, and that's why you can observe the characteristic of voltage till the current becomes zero will be like this. Okay, and during this process the loss of power, how power is exactly lost or what is the nature of power loss during reverse recovery time, you can observe. Okay, the shape of that curve here during reverse recovery, this is the power lost. Okay, and this is the natural or normal power loss. Okay, so this slide has been added with two extra parameters or the characteristic voltage with respect to time and power with respect to time, but these two are also associated with the reverse recovery characteristic. Part A is important or characteristic A is important. Okay, reverse recovery time, it is defined as the time between the instant forward diode current becomes zero, when the forward or the normal diode current becomes zero and the reverse recovery current decays to 25% of its peak value, reverse peak value, that is IRM. Okay, and the reverse recovery time is composed of two segments. As I told you, the first segment, the time between the zero crossing of forward current and the peak reverse current, is the first instant, to which we call as a TA, and the next instant is TB, the time between the peak reverse recovery current and the time at which the peak reverse current decays to 25% of its peak value. So TRR has two components, TA and TB, that I have told you. So reverse recovery charge, it is the charge recovered during the reverse recovery current time by the process of recombination of the charge stored in the depletion layer and in the vicinity of semiconducting material. This is the total charge recovered. Okay, so in time interval TA, from where the charge is recovered, from depletion layer, and in time interval TB, from where the charge is recovered, the charge is recovered from the vicinity of semiconducting material. So the softness factor, I have not explained this. The ratio of TA with respect to TB is called as softness factor. S is equals to TA divided by TB. That is not that important, but you can have one more parameter called softness factor, S, associated with the reverse recovery characteristic. Now, from that, this is just what I have told you, that there is a straight line of reverse recovery current. The straight line equation is like IRM is equals to, straight line equation is like Y is equals to mx. M is the slope, like di by dt, and x is the parameter on x-axis. Ta is the parameter on x-axis. So IRM is equals to Ta into di by dt. Now this time is very small. You can replace Ta with TRR. So you can write always. Okay. So here, this is the complete analysis of these three parameters. So reverse recovery characteristics are considered to be triangular in nature. Okay, therefore the charge stored can be estimated as QRR is equals to half into IRM into TRR. So IRM is equals to 2 QRR divided by TRR. Okay, this is just replacement of the parameters. म्हणजे दोन कन्सेप्ट या ठिकाणी वापरलेले आहेत. पहिला म्हणजे इक्वेशन ऑफ स्टेट लाईन. Okay, state line belongs to the current with respect to time. And the next concept is charge recovered is equals to area of triangle or area under the curve. That curve looks to be triangle. Okay, so you can find out the area of triangle by half base into height. So on the base there is TRR time, and for the height we have the maximum value of current, reverse current, that is IRM. So 1 by 2 into IRM into TRR. So if we rearrange the equation or rewrite the equation, we'll get IRM is equals to 2 QRR divided by TRR. Now, as I said, these times are very small. TRR can be considered as a TA. So IRM is equals to TRR into di by dt. So again, rearranging the term, we get TRR is equals to square root of 2 QRR divided by di by dt. Okay, and from the equation IRM is equals to 2 QRR divided by di by dt into square root into di by dt. Okay, so we get the peak value of reverse current IRM is equals to 2 QRR di by dt and its square root. Okay, you can write this because they ask like estimate the value of reverse peak value of the reverse current, reverse recovery charge, and reverse recovery time. So this part is for analysis of these three parameters. You can have it in your notebook. Okay, so you can take some time. रिअरेंजमेंट आहे दिलेल्या एक्सप्रेशन्सची आणि इक्वेशनची. याच्यामध्ये दोन गोष्टी आहेत. पहिलं म्हणजे स्ट्रेट लाईनचं इक्वेशन आणि दुसरं म्हणजे एरिया ऑफ ट्रायंगल. असे बरेचसे कन्सेप्ट इथून पुढे येणार आहेत कारण अनालिसिस पार्ट मोठा आहे पॉवर इलेक्ट्रॉनिक्समध्ये. ज्या वेळेस आपण एखादा कन्व्हर्टर किंवा सेमीकंडक्टर डिव्हाइस शिकतो त्यावेळेस त्याच्याशी असोसिएटेड असणारे पॅरामीटर आपल्याला फाइंड आउट करायचे आणि मग आपल्याला त्याचं अनालिसिस करायचं. मग अनालिसिससाठी मॅथमॅटिकल पार्ट हा तुमचा फंडामेंटल कन्सेप्ट क्लिअर असायला पाहिजे की ज्याच्यामध्ये डेरिव्हेशन, इंटिग्रेशन या गोष्टी येणार आहेत. शिवाय असे साधे कन्सेप्ट ज्याच्यामध्ये स्ट्रेट लाईन्स इक्वेशन तुम्हाला माहिती असायला पाहिजे, त्याचा स्लोप कसा फाइंड आउट करायचा आणि इक्वेशन रिअरेंज करून इक्वेट कसे करायचे. हे बेसिक स्किल आहे. जर तुम्हाला अनालिसिस करायचं असेल तर एवढं गरजेचं आहे करणं. यू कॅनॉट रन अवे विथ मॅथमॅटिक्स इन इंजिनिअरिंग. So there is a reference at each and every stage of your course and graduation in engineering. Mathematics is must. Okay, I hope you have done this. So the significance of characteristic. From these characteristic, what we can get. Power electronic engineers can choose the power diode if the data sheet is provided with the following parameters by manufacturer. With the help of these characteristics of the parameter like this, you can select the semiconductor device and its rating. So peak reverse current, stored charge, softness factor, it is the ratio of TA by TB, and peak inverse voltage. So you can take help of these three parameters or these parameters and you can select the device as per your requirement. Power diodes can be classified on the basis of their characteristics. So how exactly we are getting the characteristic for given semiconductor device or power diode? You can specify which type of power diode it is. Okay, that is, if we change the type of power diode, you may get different characteristics, or you may get different nature of these parameters, different values for these parameters, so that you can predict which semiconductor device you have to use. Okay, so that is the advantage of having characteristics with us. From characteristic, you can select the device as per your requirement. Now, based on that, we have the types of power diodes. Power diodes are classified according to their reverse recovery characteristic, like general purpose diode, fast recovery diode, and Schottky diodes. These are the three main types of power diode. जनरल पर्पज डायोड जो आतापर्यंत आपण शिकला, ज्याचे कॅरेक्टरिस्टिक्स आपण शिकलो, तो जनरल पर्पज डायोड आहे, पॉवर डायोड. त्याच्यानंतर फास्ट रिकव्हरी डायोड, ज्याच्यामध्ये TRR खूप स्मॉल आहे, तो फास्ट रिकव्हरी डायोड. ओके, आणि शॉर्टकी डायोड, हे तीन टाइप आहे. Now I have compared these three types of power diodes based on their ratings, applications, and reverse recovery time. So if we talk about general purpose diode, it has reverse recovery time of 25 microseconds, and its ratings are normally 1 ampere to several kiloampere, and voltage ratings are 50 volt to 5 kilovolt. Okay, what are the applications of general purpose diode? Battery charging, electric traction, electroplating, welding, and UPS. For these applications, general purpose diodes are used. Okay, obviously these are power diode, remember. I will not mention each and every time these are the power diode, not the normal diode. And that's why they are used in battery charging, electric traction, where the voltage and current ratings are very high. Then electroplating, welding. For UPS, we require power diodes, and these power diodes are of general purpose diode. Okay, their current ratings are 1 ampere to kiloampere, several kiloampere. Voltage ratings are 50 volt to 5 kilovolt, and their reverse recovery time is 25 microsecond. This is a very small time. That's why I mentioned that they have very small time. You can compare them. Okay. Then fast recovery diode, it is 5 microsecond. Now time required for general purpose, it is 25 microsecond reverse recovery time, and for fast recovery diode, it is 5 microsecond, very less. Again, current and voltage ratings are given. Now applications of fast recovery diode are chopper, commutation circuits, SMPS, induction heating. Fast recovery diodes are required where very high response of the device is required. We must use fast recovery diode. That is, it should be switched on and off very fast at very high frequency, and that's why we must employ fast recovery diode. Okay. So techniques of manufacturing: below 400 volt epitaxial growth technique is adopted, and above 400 volt diffusion. There are two techniques of manufacturing of semiconductor device: epitaxial growth and diffusion. So above 400 volt there is a diffusion, and below 400 volt there is epitaxial growth. म्हणजे जे पॉवर डायोड हे 400 पेक्षा वरती वापरले जातात त्यांच्यासाठी epitaxial ग्रोथ या टेक्निकनी डायोड मॅन्युफॅक्चर केले जातात, आणि जे पॉवर डायोड 400 वोल्ट पेक्षा कमीला जास्तला वापरले जातात त्यांना डिफ्युजन या टेक्निकनी मॅन्युफॅक्चर केले जातात. ओके, सो दिस इज वन मोर point associated with it. And the last we have Schottky diodes: lower cut-in voltage, higher leakage current, and higher operating frequency. These are the features of Schottky diodes. Reverse recovery time: there is no reverse recovery time. That doesn't require associated with the reverse recovery characteristics. Okay, so they don't have reverse recovery time. So you may assume that in that perspective these are ideal diodes. Okay, so that doesn't require reverse recovery time. Then current 1 ampere to 300 ampere, voltage up to 100 volt since reverse voltage rating. Okay, applications are high frequency instrumentation, switching power supplies. Okay, techniques of manufacturing: metal semiconductor junction, no PN junction. Okay, as they don't have PN junction. That is the basic reason behind Schottky diodes. Okay, so generally metal is aluminum and semiconductor is silicon. So Schottky diodes are the combination of aluminum and silicon. So generally we see that the diodes are the combination of P type of silicon and N type of silicon. Means they are only having semiconducting material, but Schottky diodes, they are having one one of the part as a aluminum, that is metal, that is conductor, and another part is semiconductor, that is silicon, normal silicon. Okay, so there is no existence of junction. P आणि N असा टाईपच अवेलेबल नाही म्हटल्यानंतर जंक्शन येणारच नाही. Okay, so aluminum silicon junction only, but you cannot say it is a PN junction. It is aluminum silicon junction. Okay, and its physics is something different. So that's all for today. Now I'll call your phone number. You have to unmute and give your attendance. 401 02
Present, sir.
3
Present, sir.
4
Present, sir.
5
Present.
6
Present, sir.
7
Present, sir.
8
Present.
9
Present.
10
Present, sir.
11
Present.
12 12 13
Present.
14
Present.
15
Present, sir.
16
Present, sir.
17
Present, sir.
18
Present, sir.
19
Present, sir.
20
Present, sir.
21
Present.
22
Present.
23 24
Present, sir.
25
Present, sir.
26
Present, sir.
27
Present.
28
Present.
29 29 30
Present.
31 30 आएगा
Present.
31 32
Present.
33
Present, sir.
34
Present, sir.
35
Present, sir.
36
Present.
37
Present, sir.
38 38 39
Present.
40 40 41
Present, sir.
42
Present, sir.
43
Present, sir.
44
Present, sir.
45
Present, sir.
46
Present.
47
Present.
48 48 49
Present.
50
Present.
51 51 52
Present.
53
Present.
54 54